Everybody, thanks for joining us for this new session of the Victor online course. So today I have the pleasure to have Shuo Ding. She's an assistant professor at University of Florida, and she's working on thermodynamics and modeling of volatiles and volatile fluxes on volcanoes. And she's going to show us one of the tools that is available on Victor for modeling gases that is called Sulfur X. So, as usual, if you guys have any questions during the presentation and the activities, don't hesitate to raise your hand or write in the chat, and then we're going to be able to address your question. So yeah, thanks, Shu.
Yeah, so I'm gonna share my screen. Can everyone see it?
Yep.
And the cursor too?
Yep.
Yeah, cool. Yeah, hi everyone. Well, thanks Sivan for having me, and thanks Einat for having me again on this course to talk about SolveX on Victor. So since I know like this course is for a pretty broad like people from different fields in volcanology, so this I will introduce very quickly about the mechanism of sulfur volatile degassing and SolveX, this model, and then I will go into the just basically open Victor and run SolveX. So there are different scenarios I plan to run, like closed degassing, open degassing, and if we're interested in tracking FO2 change, in the magma, and then maybe talk a little bit more about in the end of the application of how do we use this degassing model to interpret the gas composition. All right, so it doesn't go. Maybe I forwarded. Sorry, my slides do not advance. Okay, all right, yeah. So first of all, when we talk about magmatic volatiles or modeling, I think the water, CO2, sulfur are like the three most abundant volatiles in the magma, and they're actually in different level of concentration. Water, we usually talk about weight percent. And the CO2, we used to think it was only like at the ppm level, but now as the advancement of measurements, and we realize, okay, some magma can actually also have like weight percent level of CO2. And then we have some other less abundant ones like sulfur and chlorine. So they're usually at like thousands of ppm level. Of course, all this concentration depending on what type of magma that we're looking at. And melt inclusion, which I'm going to show a picture later, is basically one way for us to really measure the volatile concentration in the magma at pre-eruptive stage. So the reason why we are interested in volatile is because they are actually the dissolved volatiles. For example, water can have significant impact on melt viscosity, and the formation of these vapor bubbles can actually really affect the magma compressibility and the buoyancy. Therefore, it actually studying volatile is really important to understand the eruption dynamics, and also it's very useful to understand the plumbing systems underneath the volcanoes. And then there's another topic have been recently advanced a lot is really to use the volcanic gas. So modeling volatile degassing can really help us to interpret volcanic gas and to see if volcanic gas can be used as a eruption precursor. So when we talk, so here is the sketch about like magma from high pressure to low pressure during magma ascent. So right now, I think I think all of the volatile degassing model, when we talk about it, we're really assuming the vapor phase is in equilibrium with the magma during the ascent. So the stage we're really modeling is the pre-eruptive stage before the fragmentation happens. So, and also we assume that all the vapors are in equilibrium with the magma. So that's like the condition, the assumption we're making here now. So as magma ascend from high pressure to low pressure, volatile would exhaust to form these vapor bubbles. And depending on what type, so how much volatiles and what type of volatiles exhaust depending on pressure. That is because at least for water, CO2, and sulfur, the solubility, basically the maximum amount of these volatiles can be dissolved in the magma, is actually very pressure sensitive. So for example, if the magma, if it's at depths, CO2 actually comes degas very early. So at depths, the vapor bubble we would expect is very CO2 enriched and less enriched in water and sulfur. So because of this pressure sensitivity, right? So if the analysis of water CO2 in the magma or in the melt inclusion can really help us to constrain the depths. So this is a picture of melt inclusion. So this is basically a melt inclusion sitting in an olivine. So this melt inclusion is like it's like a melt parcel that's entrapped during crystal growth. So this actually helped the volatiles from degassing away during the eruption. So it can really tell us the information about how much volatiles could be in the magma at the time when it was entrapped. So if we have melt inclusion entrapped at a different depths, and by analyzing these volatile contents in the melt inclusion, we can actually have a record of volatile degassing during magma ascent. And again, if we measure CO2 and water in this melt inclusion and then calculate this, the saturation pressure, so that can give us pressure information of the plumbing system. And then if a melt inclusion is entrapped really deep, or if we analyze a lot, so the least degassed melt inclusion can really give us information about volatile concentration in the parental magma. Okay, so then after usually what people do is, so we collect the data and then we were interested in to also model if, to see if we could actually reproduce the melt inclusion record. So that means maybe the change of volatiles we observed through melt inclusion is due to degassing. So in order to model, so we usually model volatile degassing by model the solubilities of different volatiles, right? So that is usually a function of pressure we just mentioned, but then also temperature, melt composition also matters. And for sulfur, oxygen fugacity is another very important parameter to affecting sulfur degassing. So the formulations for volatile solubility model can either be thermodynamics or empirical, but in either case, these degassing models are usually calibrated using experimental data. So we basically ran experiments at high pressure temperature with a controlled condition. So one important thing when using any degassing model is to make sure your melt composition is actually within the calibrated range. And also the pressure temperature condition it's applying to is also not too far away from the calibration range. Okay, so for water CO2, there are a lot of solubility models available from the early ones like 1997, the volatile calc to more recent one. And this VasiCalc is a really good package to summarizing all the water CO2 degassing model. And I think VasiCalc can be pip installed, so it's pretty easy to use. So if you are only interested in these two volatile species, you could VasiCalc would be a good platform, and you can choose among all these models. Okay, so let's talk about sulfur. So sulfur is a bit more complicated than water and CO2 because when we are thinking about sulfur degassing, it's not the elemental sulfur. Sulfur is a is a multivalent element, so it has different valence states. So in the melt, it can exist as sulfate or sulfide, and in the vapor, at least the most abundant ones would be hydrogen sulfide and sulfur dioxide. So when we talk about sulfur degassing, what we're at least looking at two different reactions here. So one is the sulfides degas as H2S in the vapor, or sulfate degas as SO2 in the vapor. So because of these, oxygen fugacity really plays a really important role in modeling, in understanding, and also modeling sulfur degassing. And also we can see is the second reaction actually involves redox change, right? So from S6 plus degas into S4 plus. So this is actually also important because now we have realized this sulfur degassing might have also played a really important role in the redox evolution of magma. So sulfur, I think before maybe 2020, there were pretty limited model, and the conventional way of thinking sulfur degassing is really like it degas very late. So the solubility kind of follow this trend. It only decrease at very shallow pressure. However, I think recent 5 years or 6 years, there's a lot of new sulfur degassing model coming out and taking into account the FO2. And then we really realized, okay, so sulfur degassing can be complicated and can be very diverse, can degas early or late, depending on the FO2 concentration and also water concentration. Okay, so here's the sulfur X model. So which we published this. These are my co-authors from GCube at GCube in 2023. So basically, it's a model to predict the evolution of these three volatile sulfur, CO2, and water in the basaltic magma or basaltic andesite, and also in the coexisting vapor. So the way we do it is we actually we use the existing CO2 water degassing model and then combine with the new developed sulfur degassing model. So the unique thing for this model is it can track the redox evolution during sulfur degassing. And we used the way we did it is use the redox budget conservation among sulfur and iron. So we are only thinking about, we are assuming only sulfur and iron can change valence states in this whole process. Okay, so just a little bit about sulfur partition coefficient. So this is the key component of sulfur X model. So there are other sulfur degassing model, and they use different side, like they could use sulfide or sulfate capacity model. So it's all so this is really different ways of describing the sulfur behavior during degassing. So here we're using sulfur partition coefficient. So partition coefficient by definition between vapor and melt is basically sulfur concentration. It could be melt weight percent. It could be mole fraction. So in sulfur X, we're considering mole fraction. Okay, the concentration of sulfur, a mole fraction sulfur in the vapor, and then divided by the sulfur concentration, sulfur mole fraction in the melt. So instead of just using one partition coefficient for sulfur, we are actually considering sulfur degassing as two separate reactions here. So one reaction is sulfide degas to H2S. So we use existing experimental data to constrain the sulfide partition coefficient of reaction 1, and then we define reaction 2 as sulfate degassing to SO2. So in this way, we can use existing experimental data to constrain the sulfur partition coefficient for reaction 2. And then in the degassing model later, we will combine these two reactions by the sulfur speciation in the magma. So this figure is just one of the figures from the 2023 paper showing how sulfur speciation, this red thing, can change with the FO2, and how partition coefficient could also be a strong function of FO2. It first increase and then decrease. So that's why it's really important to consider these two degassing reactions separately. But then later we also the temperature, pressure, and melt composition, all these would affect the two sulfur partition coefficients, and therefore affecting sulfur degassing. Okay, so that's only the sulfur behavior part. So in sulfur X, then we combine this together with the existing CO2 water degassing models. As I mentioned, there are several. So here we provided two options. So I recommend in general, we choose this one because this is calibrated in a wider pressure range. But the second one is really really for kind of shallow pressure, low pressure, and also is more important is in a dry magma. So if you are interested in like the modeling arc magma degassing, which has more than 1% water, this one would be more suitable. And then since we need to know what is sulfur speciation, basically sulfate over total sulfur ratio in the magma. So we need some models to connect between sulfate over total sulfur ratio to ferric ion ratio in the magma. So there are existing models describing this relationship. So we provided choice of these three. I think newer study basically show these model might have actually overestimated the temperature effect. So I recommend use this one, but you could also use the Muth 2021. And then again, we need also to calculate the absolute oxygen fugacity. So we use this very classic Kress and Carmichael 1991 model to convert between the ferric ion ratio to the FO2. Okay, so this is just like one of the results figure from the SOFAX paper. So I just want to quickly show is how, so this right panel basically described how different sulfur speciation and different, so these numbers is the water concentration. If we look at a reduced situation with only 10% sulfate in the magma, and if the magma is also dry, we can see that the sulfur degassing happens really shallow, which is kind of the conventional way of thinking about sulfur degassing. However, if even for a reduced magma, if we add water, right, 2 weight percent, 3 weight percent, 4.5 weight percent, then we can see the sulfur, the pressure that sulfur is degassing significantly, actually getting deeper and deeper. And then if the magma is relatively oxidized, so sulfate over total sulfur ratio 70%, and then we can see even it's a dry magma, sulfur degassing can happen actually deeper compared to the reduced dry case. And then again, adding more water make the sulfur degassing earlier and earlier. And then this is a table in the paper. The important thing is sulfur X is now, sorry, this is the table. It's now calibrated for basalts and basaltic andesites. So these are all the experiments that go into the calibration. So do keep in mind if you decided to use it for dacite or rhyolites, these sulfur X might not be for it. There are less models to modeling the more felsic composition. So that's definitely a need. Yeah, so that's that. So this is the pressure, temperature range. So for sulfur degassing or experiments in general, there is a lack of high pressure experiments here. Okay, so that's all the degassing mechanism. So we can now go to, I think we can now go to Victor to play with it a little bit. I don't know how can I stop share. Okay, here we go. Okay, so yeah, now everyone can see the Victor, right? Okay, cool. So I think I installed it like this morning, so I already changed some of the parameters, but I
Let me
think
just Let me just say that in order to get access to the to this notebook, please go into the terminal and type the command line Victor setup, like we did for the other models, and you should see SulfurX in the list of the models. So just
Yeah.
click on the number that corresponds to that, and it's going to install a new folder in your directory that is called SulfurX, and you should be able to get access to the notebook.
Yeah, thanks for adding this. Yeah. So this is, I think, the what Savan was talking about. You need to do the setup thing and then install. Anyway, then it will appear here. So this is my SulfurX model, and now I can open this notebook. So it's this one. Yeah, I think the first time before you ran anything, there's no results folder. Yeah. So, but I try to return to whatever when it was installed. So now we can actually by looking at this, we can also look at some of the main parameters that's needed to input. So here is basically some basic parameters here on this. Can I make this bigger? Maybe no. Okay. So basically temperature. So I think it was, I guess if we're looking at the basalts, it's a little bit low. So let's just do like 1100, but you can leave it like just input whatever temperature you think the liquidus temperature we're looking at, you want to model. And then FO2, this is relative to the FMQ buffer. So here, I think we can leave it at 1.52. And then this is initial water concentration. So this is basically you need to, since we're modeling decompression degassing, so this would be the highest water, CO2, and sulfur concentration you think this magma could have, like pre-decompression. So then when SulfurX runs, it will actually change, so it will first calculate the saturation pressure. So that would be the starting point of the decompression modeling. And then it will decrease pressure and the space, like how each step, how much pressure decreases, we can choose it later. So okay, so this is the initial volatile concentration. And then this is crystallization. SulfurX currently does not have a great way to implement crystallization function, but it can take into account the composition change due to crystallization. So for now, we could just say we disable crystallization, but we can run it afterwards if we want crystallization. But it does not calculate the crystals that are coming out. It only the way they account for it is basically to change the composition as the degree of the melt change. Okay, so this is how we can adjust this L, is how we can adjust the pressure step during decompression. It's just by telling SulfurX, okay, from the initial pressure to 1 bar, how many steps you want to run. So you don't tell it like the incremental pressure, but instead you tell it, okay, how many steps you want to run. So 1,000 is kind of high usually, and takes longer to run because it will need to run like more times. So usually I will start with 300, but there might be cases you need to adjust this, which I'll come back later. Okay, so here, we need to specify some of the other models. So because I just talked about in use, right, it combines with the CO2 water degassing model. So as I mentioned, I recommend normally we use the Icano-Marciano model, which is 0. And if we want to choose the volatile calc, that you just put a 1. So there are a lot of like 0, 1 input things in this code. And then the sulfur speciation, basically to link the sulfur speciation with iron speciation model. So we have NASH, which we said I recommend actually to use O'Neill because NASH might be actually overestimating the temperature impact. And or you can change to Muth model, which is 100. So then do you want to change FO2 or not? So yeah, I think like if you are interested in modeling FO2 change, eventually you can, so of course we will choose yes, right, which means 1. But if you are actually modeling a data set that is very new, my recommendation would be first, we choose 0. So we turn off the FO2 model, but then after we adjust the other parameters, and then it can give us a reasonable degassing trend. Then after that, we turn it back on to model the FO2 because modeling FO2 might actually require some other parameter adjustment. So it's better to have our baseline first without FO2 change. Okay, so here is basically, there is option, but I think it really require going to this main file to change this is the main function file to change, but there is option of, oops, where am I? Yeah, there is option of actually reading a multi-inclusion file, multi-inclusion data file, and then make the plots. So that's why this is here. It's really for if you want to compare to your multi-inclusion data. And then there's this the output file, right? So we can just say first run. So this is the output name. You can say anything, and then later output would be the results folder. It will be output into the results folder, and then save image. So this is the specifier of the Monte Carlo. So this is for how can SoftX actually account for uncertainties. So it only accounts for uncertainties for the sulfur partition coefficients that's developed in this study, because those partition coefficients have pretty big, well, not pretty big, like 15 to 20% uncertainties. So the way is you could actually ask SoftX to run multiple times, and each time it would actually randomly choose a partition coefficients within the uncertainty. So then it will output the multiple modeling of the results of all the Monte Carlo simulation, and also the average and the mean and the standard deviation. But this one also I suggest is after everything, you modeled everything and everything looked really good, looked satisfying, and then that's when you actually turn it on. And then you can, so if you want to turn it on for 1, if you want to turn it off, this is 0. And then if you want to turn it on, so this is basically how many times you want to run it. So I usually run it like 1,000 times or something. If it's more, it will take up. I actually, yeah, I don't know how long it will take on Victor actually, but yeah. So if the more, the longer it will be. That's basically. So then there are some other parameters we can set. So for example, this one. So this melt fraction is actually just the initial input, so you just leave it as 1. So this incremental thing is because sometimes SoftX might have issues when it ran to like really low pressure. So if that's the case, and if like basically like the last 50 bars or something. But if you only want to compare to the melt inclusion data, and the rest actually looked pretty good, so you can actually choose to turn off the modeling before it reach 1 bar. So that is when that is where you can put the bar thing. So usually I will leave it at 0. And so this increment thing is basically, okay, I still wanted to continue running, but after this certain bar, what I wanted to do is to actually just increase the partition coefficient by a arbitrary number. Like, let's say, assuming you know that the partition coefficient at surface by based on the gas measurements or the matrix glass concentration of the sulfur, is about 1,000 or 2000. So then you can say, okay, I want to incrementally, below this pressure, I want to incrementally increase 20 or 50. So that would be basically you are arbitrarily telling it to change the partition coefficient. Yeah. So usually it will run to this. It will run to the end with no problem. So I usually do not really use this. Okay. So here is this sulfide composition is really about using it to calculate a potential sulfide solubility, basically instead of degassing. Another likelihood to sequestrate sulfur is actually forming sulfide. And the sulfide solubility, and when the and this, if you are looking at a really reduced magma, there is a possibility that it could form sulfide. So sulfur X does not really take into account of sulfide formation during degassing, but what it does is you can actually input the potential sulfide composition here, because the sulfide solubility is related to how much copper and nickel could exist in the sulfide. So you input this, and then it will calculate the sulfide solubility change along degassing as well. So you can compare to see, okay, how likely is that the modeled sulfur concentration in the magma is always higher than the sulfide saturation value, if that or lower. If it's kind of lower, then you're safe from sulfide saturation. Okay, so then this sigma thing, it is a tolerance of how much FO2, so and this is only relevant for calculating FO2. If you are interested in the magma redox change along degassing, that's how you can do it. So this, we can change it usually depending, and so this one is when it calculates the FO2, it will iterate, it will look for the best, like the FO2 that satisfy all the conditions by a lot of iterations. And the iteration will stop when the FO2 difference is smaller than a certain value. So this is our value we're looking at. So this is in log 10. So basically, if it's, I think this value can be as high as 0.1. I mean, it really depends on, right? So if even it's 0.1, it's still kind of within the measurements uncertainties there. So we would not be able to, based on our current technique, it will be difficult to actually differentiate the FO2 smaller than 0.1. So, but then this is actually a very important parameter you can play with when we calculate FO2 change. And these two are really relevant for if we want to look for crystallization, since we are unable dislabeling it right now, so we could come back to this too. And then okay, so then there is the initial sulfur isotope, the delta 34. So this is kind of a newer function. It's not included in the 2023 paper. So this is basically based on the sulfur degassing. It can also model the sulfur fractionation during degassing. So it can calculate the D34 change in the magma and the delta 34 change in the vapor phase. But it does require the input of the initial D34 value in the magma. Okay, and then here is another new function compared to the 2023 paper is now we can, it was only for closed degassing before, but now we can also do open degassing. So the way this works is if we do 0, so basically this input is required is for at what pressure do you want to start open degassing? Because we know like sometimes the degassing can maintain close until magma ascend to a certain level and then become open degassing. So if we say 0, that means it never opens, right? So that means we're modeling close degassing, but we can put, let's say 200, and it's in megapascal. So that means we were modeling from a certain pressure, the saturation pressure, ask the magma to degas until 200 megapascal, and then you switch to open degassing change. And in this case, if we do use open degassing in the results column, you can actually see the instantaneous gas composition and the accumulated gas composition. Okay, so now we can make it just close for now, so that's 0. Okay, so I should have run it all the way. So let's do this. We can just run it. Okay, so here it actually would pop up something. So so basically it will tell you what is the calculated initial vapor saturation pressure, and then what is, for that vapor, what is the concentration, what's the mole fraction of the water and CO2. So when finding this initial vapor saturation pressure, SoftwareX only use water and CO2. And then at the next step, it will partition sulfur into it. And then you also calculate the initial ferric iron ratio. So we use the FMQ 1.2, so it convert to 23% of ferric iron. And then based on this, it tells you what's the initial sulfate ratio in the magma is. So we're looking at almost 85%. So, okay. Is there, so yeah, so then the reason why I actually had this printed out is because I realized, so one thing is it can tell you, okay, at what pressure, if that is not what you expected, if you have some other independent constraint, and so then we might need to go back. You can quickly, without running the whole model, just go back to adjust maybe the initial CO2, and also, or maybe the degassing model, the water CO2 model you're using. And the same thing for the ferric ferrous iron ratio, because there are different ways of convert. So because some people would have the ferric ferrous iron ratio of the magma, but some others may not have that ratio, but instead have the relative FO2 relative to FMQ buffer. So this is a way for you to actually double check, is this the ferric ferrous iron ratio you are expecting? If not, you might want to adjust your FMQ value to actually match whatever, if you measure your measurements, right? And then it will also tell you, okay, another check would be, do you expect your magma actually have more than 80% sulfate? Is that reasonable? If not, maybe you would have to go back. If you measure the sulfate ratio instead of measure the ferric ferrous iron ratio, then you might want to go back to adjust this DFMQ. So to kind of match what the ratio you actually measured. But if everything is good, then we can say yes, and then it will continue run the model. Yeah. So any questions so far? Sorry, I just kept talking.
I don't see any question in the chat so far, so.
Okay. Yeah.
Looks good.
Cool. Sounds good. Okay. Okay. So yeah. So this is basically just some output, which is mostly try to match the figures I actually put in the 2023 paper. So, but it also give you a quick visualize of what you model depending on what you really want to model. So for example, this is modeling sulfur concentration change as pressure. So right, we can see it actually starts degassing relatively early, and it also kind of give you an idea what is your vapor saturation pressure. This is how sulfur delta 34, the isotope change as in the melt as sulfur decrease. And we have sulfur versus CO2, water versus CO2. These are like typical volatile plots. People are interested when we're looking at volatile concentration in the magma. And then here, the last one is actually how sulfur, CO2 over sulfur ratio, the molar ratio in the gas change as pressure change. So this one, it's of interest if you want to actually compare to your measured CO2 sulfur ratio in the volcanic gases to infer, okay, where does this gas come from? So this would be a relevant figure. Okay, yeah, so I think, so basically we can do that, or if we, instead of closed degassing, we want to do open degassing, we can say, okay, we want to open the degas at 200 megapascal. I think it will look slightly different because the degassing style change. So we can see there's a kink at 200 megapascal. That's because the degassing, now it's modeling open degassing. So I think, so this is how the sulfur, so it does matter for, right? So the sulfur isotope change actually changed. It doesn't, so that's one thing actually can actually make a significant difference between open and closed degassing is the sulfur isotope ratio. And then we can see also in the gas ratio, there is a kink too. So yeah, so that's the open closed degassing. You can say I wanted to open later or sooner, that's all fine. I think, let me see. The next one we can talk about is, oh yeah, before I forgot, another important thing is let's take a look at the results heading before we go into more models. Yeah, so the results heading, I think, so this is basically, it has explained in the explanation in the supplements in the 2023 paper. But here we can quickly go into some stuff we're interested in. For example, this is the pressure. So the degassing starts at 537 megapascal in pressure in megapascal, and that is basically the saturation pressure sulfur X or the CO2 water rate model use the initial water and initial CO2 to calculate it. So these three are some generating interest is the weight percent. So W means weight because it also output the mole fraction later. So the weight percent for water and ppm for sulfur and CO2, they're in ppm. So another potential interesting, yeah, so I think that's the interesting output. Another interesting output would be what is the sulfate, right? What's the sulfate over total sulfur ratio change in the magma? So this would be the S6 plus over ST. And then it also models the sulfur speciation in the vapor, in the gas phase. So that's another interesting thing you can compare to the gas data, right? Because very often we could measure if it's SO2 or H2S, even though the gas data could be monitored by, could be modified by the hydrothermal activities. But so here it will tells you, okay, what's the percentage of SO2? And note, we are assuming that there's only two species in the gas for sulfur is SO2 and H2S. So we're ignoring like other minor components here, sulfur bearing components here. And we can also look at, this is the ferric ion ratio. So this is basically the Fe3 plus over total ion. That is another thing people very often interested in comparing. And here is the calculated sulfide saturation value and sulfate saturation value. So this is only for comparison to say, okay, am I in the danger zone of actually hitting the saturation value? What else? Yeah, and then, oh yeah, so here, this is the accumulated CO2 over sulfur ratio in the gas. So that's one thing we are interested in. And this is the isotope change, D34 change in the magma. And then there is also the accumulated D34 change in the vapor. And this one is the instantaneous D34 in the gas, the D34 of the instantaneous gas. And here is the sulfur isotope fractionation factors, alpha. So basically, yeah, so these are some relevant output items here. Okay, so we can go back to yeah, we can go back to this. We covered, oh yeah. So now we just turn it off FO2, right? So if we say, okay, we're happy. Okay, let's first turn off the open degassing thing. Now we're happy with our, we're happy with our calculation without FO2 change. So now what we want to do is, okay, I actually want to track FO2. So here we can actually turn it back on to see to this one. So now we can actually see how FO2 will change along sulfur degassing. So that's why. So before, when we turn it off, this would be a straight line because we fixed the FO2. But now this figure is basically showing the model delta FMQ. So we can see in this scenario, right, we have our FMQ first increase as degassing, but then in the end, it kind of winded back. So here in this figure, it basically gives you the results, well, how the soft ion speciation change, and then how the SO2 over total sulfur ratio change. So it will increase all the way to 1 bar, and then how the sulfate over total sulfur ratio change. So it first increase and then decrease. So kind of follow this trend and this ion trend. And then we can see our, again, the sulfur isotope fractionation actually matters a lot, like how the FO2 matters a lot. So now we are seeing a different shape. And then this is, again, sulfur, water, CO2 concentration and gas ratio.
We have a question
Yeah.
about what is FMQ.
Oh, it's actually a oxygen fugacity constrained by mineral assembly. So it's the fayalite, magnetite, and quartz. So basically, when these all in equilibrium, what's the oxygen fugacity for this reaction? And because these are common mineral reactions, we use it as a reference point. So instead of talking about 10 to the minus 14 log for oxygen fugacity, we're talking about how many log units we are away from the equilibrium oxygen fugacity set by this reaction. So it's a very commonly used one. People can use other ones, so like nickel oxide, or hematite, magnetite, which are more oxidized. But FMQ would be a good one to model in like covering the different magmatic settings on Earth. Yeah. So we can do like +1, +2, or -1. That would be mid-ocean ridge basalts.
Thanks.
Okay. So any other questions?
Well, I have one actually. So let me put my camera on. So I'm interested in the sulfur dioxide content and how would you actually compare the model sulfur dioxide content that you have to like an observed one from monitoring? Because I know, for example, Roberto, who's one of the participants of the course, he's a member of INSIBUME in Guatemala, and they, correct me if I'm wrong, Roberto, but I think you guys just installed a SO2 monitoring capacity at Santiaguito, I think it is. So I was just interested in, how they could actually use this model to actually compare the observed values that they have from the monitoring to the model value that they get from the code. So can you talk a bit more about that?
Well, that's a great question. So if you are looking at SO2 flux, I think it requires other information here, because what it really models is the concentration or mole fraction of the gas, but we don't have the magmatic flux here. You have to make assumption like, okay, how much magma, right, is actually ascending and degassing. I guess you can maybe make some, that would be actually a difficult parameter to constrain. Or this is something I've been thinking and working on, like one very prelim thought would be maybe it could be actually a free parameter for software X to look for. We just run it a lot, and then to see what would match the gas flux.
Mhm.
And then you can actually back constrain, okay, how much magma could potentially be degassing at this moment or something like that. So
Right.
I think that's like one of the things I'm thinking about, like I'm actively thinking about developing, because I know there's so much SO2 flux data. It would be really good to really use it for the model. But at this stage, another thing we could compare it to is the CO2 sulfur ratio. That's another commonly used gas data. So that is actually something we have been using. So I could show this very quickly. So this is basically a paper we had out recently in last year. So this is basically the CO2 sulfur ratio data from Turrialba volcano. So you can see that kind of give us, so people have measured CO2 sulfur data is kind of stable, but then these are the eruptive events. It always goes up just before eruption. So this CO2 sulfur molar ratio, we can compare to our model. So this is our model results. This is closed degassing, open degassing, or open all the way from the beginning. And then we can compare this modeled ratio, right? And then to what we actually observed. So this is what we observed in the gas. This is the distribution. So it's around like 2.3. And then that, actually by using that, we kind of inferred, okay, this might be a magma stalling region. So basically you have magma kind of ascend and then stalled there and then continue degassing. That's what is really create this kind of, we call it quiescent degassing. So just when it's not erupting, it's just constantly degassing. This could be, yeah. And then we also modeled, okay, how can we match the higher value? So basically this high point, just right before eruption, we will see we saw a significant increase of CO2 sulfur ratio. So this is around 10. Of course, there's some even higher. So then we compare to our degassing model. We say, okay, this gas actually has to come from like at least 12 kilometers deep. So, or even higher. So that's one way. That's one possible way we can use it. But there's still needs a lot of there's still a lot of work can be done.
Cool. Yeah, Roberto is asking if to measure the CO2, you will need another sensor, or you will need one of these multi-gas sensor to actually measure the CO2 at the same time, or can you derive it from the SO2 data?
You mean what is the CO? Is that in the chat?
Yeah.
Oh, no, I think, yeah. So you usually the CO2 sulfur ratio, what we do is really to measure using multigas to measure the ratio. So CO2 flux is actually I think people have been deriving the CO2 flux by combining the ratio and the SO2 flux. And that is because CO2 flux itself is it's difficult to measure because there's a lot of CO2 in the air. The background value is just too high. But I think right now, like there are groups are measuring CO2 flux, but it's more difficult than SO2.
Cool. Right. Is there any other questions? All right. Is there anything you wanted to add to? That was really good. Really, really nice presentation.
Thanks. Yeah, I guess one thing I don't know, like I actually have question like about software X. I guess I could because I did encounter this when I played with it. I could maybe talk a little bit with you guys, so you guys could let me know. I think is so I was changing some of the functions here, and my understanding is if I change anything here, it will be okay, right? Like
That would be a question for Sam. I don't know if Sam is here.
Yeah, actually, I
I'm
guess.
here.
Oh, great.
Okay. So the question is if you change anything in that main Fuego file, is that okay? Or
so right now the way I have it is a little bit hard coded by line. Like for the main Fuego, all of the input parameters, it's just basically replacing that line.
Yeah.
So if it was just that, it should be fine. But if you're adding lines, then it probably throws everything out of whack. It's probably time for me to come back to this and make a slightly cleaner version, but um, it depends on what exactly you mean by like adding to the
Yeah.
main Python file.
Actually, one thing I could measure, which is also related to actually using this, is if we use, and that's the first thing I wanted to change in the first place is, so when we run SoftwareX, right, it will have to find a saturation value. But by finding that, it actually use a initial, for the Incano-Mazziano model, it use a initial input. And that is actually embedded in this one. So basically, if let's say if we have a really high CO2 magma, that would be saturated at much higher pressure than 400 megapascal. It will not be able to find the initial pressure. That's when I actually came here. Okay, I'm gonna change this initial gas. So maybe, but then I realized one thing. I realized is I just changed this. It shouldn't affect the line number, but it takes a while for the system to realize this input is changed. Like, I don't know how long, maybe 5 minutes or something, or shorter. Is that the case, or?
When you say it takes time for the system to realize it's changed, what do you mean?
Okay, I can do it right now. So let's say if I change, oh, what did I do? Okay. So for example, if I change it here to 700, and then I go back, right? All I need to do just to rerun this cell. And then, but well, I guess not at this point, we don't really know if it read it or not.
Yeah,
oh
it's
yes,
probably.
Yeah.
Yeah, it's because you can just say overwrite, but because you're overwriting the file, you're overwriting something in the main notebook, and you also have the file open. It's just saying, hey, just so you know, the file changed. Do you want to keep the version that's currently like the old version that's currently open, that you have like on the rightmost tab, or do you want to have it overwritten?
Okay.
Yeah, the problem with running the cell above, after you made that change, is that it's overriding everything you just did. So you should just run that final cell with the run command.
Oh, okay, got it. Yeah. Okay. 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 Now it seems like it's still ran. Yeah, but so basically my point is sometimes if the magma, is very CO2 enriched, you might have to change this parameter. Maybe we should maybe make that in the workflow. That would
Sure,
be
absolutely.
Yeah, one of the input in the workflow.
Yeah, if you want to make a couple of notes on pain points that because we want to showcase your model best as possible. So just let me know and I'll make the changes.
Yeah, thanks. Yeah, and yeah, that's it. Yeah.
Cool. All right. Well, thank you very much. It's time to leave. So thanks everyone for joining, and as usual, I'm gonna stop the recording and then